Hello, my name is Angus Conley and I'm the product manager for our Flexcom software. So today I'm going to give you a very brief overview of our Flexcom Wave software. At the moment we're looking at a blank project workspace on screen, so the first thing I'm going to do is I'm going to open up one of the example projects. You can find a range of examples under the help menu. So let's just look at the first one there. It's called the floating dual body point absorber. I'll just switch on the model view from the view menu so you can see what the model looks like. So it's a dual body floating point absorber. There's a float which sits on the ocean surface. You can see that in yellow on top there, and that sits on top of a spar buoy underneath, which in turn is moored to the seabed using mooring lines. So let me just move that a little back there. So at the moment I'm looking at the simulation component, whereby I've selected the floating body dual point absorber as the device under consideration. I've also selected a sea state location called Eureka, California. Flexcom Wave is highly modular, so although this model is quite simple and I've only got a handful of components in the project view on the left hand side, you can build up quite a very detailed description of a project with lots of different devices or different sea states contained within the same project, and from that library then you can pick and choose the components that are of interest to a particular simulation. So the simulation component itself is what we call a higher level component, in that it references other subcomponents. In this case there are only two. So if I was to have a quick look at the floating dual body point absorber component itself, again this references other components such as the power takeoff component, the upper float which is called float, the lower one which is called spar, and obviously the mooring lines then, which again I can select. Because I've only got one mooring line defined in my project workspace, I just have one selection option there, but if I had more I could select from different types of chains or wires or ropes or so on, and the anchor locations. So the model is constructed using the floating body component, the dual body point absorber component, which in turn references several subcomponents, for example such as the float. So here we see the basic inputs for the float, the yellow part we see on the model view on the right hand side of the screen there. You specify its dimensions, basic structural properties like its mass, its hydrostatic stiffness, which simulate buoyancy forces, and also coefficient matrices, which define the hydrodynamic loading on the floating body using based on radiation diffraction theory. So once the structural model is completed, you then move to the environmental the loading on that structure in a particular geographical location. Here we've just got one location. It's called Eureka, California, and I should mention also that because Flexcom Wave is coupled to another product called Exceedance Finance, we have access to an online database of sea states right across the globe. So if I was to log in to the Exceedance cloud version, which I can find under the file menu, if I type in my user credentials there and log in, then I will have access to a lot of different sea states. We'll show that in another tutorial later on. For the moment, let's just look at the California site. So we can see it's a wave scatter diagram which defines percentage occurrences of various combinations of HS, that's significant wave height, and in this case energy period. And you can see there's color coding to highlight which sea states are more prevalent across the range. Once some basic inputs are defined like water depth and seabed stiffness, then you move on to the simulation, which is where I started when I opened up the project workspace firstly. For all of those sea states, or a selection of those sea states in the scatter diagram, you can perform time domain simulations using Flexcom Wave. You would do that by initiating a batch run here using the run button, which I won't do now on screen as it would be just too time consuming for the video, but I can show you results from models which I have ran previously. So let me just show you those. So the main output from Flexcom Wave is a power matrix which defines the electrical power as a function of incident sea state for the range of cases we're looking at in the scatter diagram. As well as the power matrix, we present an AEP, annual energy production value, in megawatt hour by combining the power matrix with the wave scatter diagram which we saw previously here for the Eureka site in California. Though that power matrix data is then, or may then be exported back to the exceedance product, where a financial assessment, a financial appraisal of the commercial feasibility of this device in this particular location may be undertaken. And again, we look at the exceedance product in another tutorial. For now, let's just close out the overview of Flexcom Wave. So let's look at some additional information from Flexcom. For example, let's look at the structural animation on screen. I'll just zoom in a little bit so you can see. I'll press the play button, so we have an animation playing. Let's speed it up a little so you can see hopefully some movement. Also maybe split screens if you wanted to. You can see two different views at the same time. You can maybe look at an underwater shot and an overwater shot. So hopefully you can see the float there just moving gently up and down the top of the spar buoy in response to wave loading. So Flexcom can, as well as estimating the power, obviously it can predict device motions and stresses and strains in structural members. So let's just maybe look at one or two of those as well. So back to some of the results. I'll just open this spreadsheet here. There's a summary spreadsheet which summarizes all the results in the load case matrix we've looked at for the HS-TZ combinations. So for any parameter that you're interested in, for example, I'm looking at mooring line tension here in kilonewtons in the first mooring line. It tells me what the max and min tensions are in each of the mooring lines. So if I go right down to the end of that spreadsheet, for example, I can look the fairlead tension in mooring line 1. The maximum value it reaches is this number here, 783. And this corresponds to this particular sea state. So there's a lot of potentially useful structural information which stems from the Flexcom Wave simulation, in addition to the electrical power matrix. I won't save that spreadsheet, I'll just go back in. Here I'll just look at one or two plots as well, just to show you the capabilities here. The plotting module will just load up for me now. And here's a 3D plot of electrical power. So power in kilowatts as a function of the sea states. We've got TE on one axis and HS on the other, and that's a fully 3D plot, so you can zoom in and do what you need to. These 3D plots are very useful for putting into financial or engineering reports, because they look quite visually impressive on screen. So we've looked at the power matrix, the structural animation, and some very quick sample of results. So I think that concludes the overview of Flexcom Wave. In subsequent tutorials, I'll go into more detail in terms of how you actually build the models and run the simulations and extract those results. But for now, I hope that's quite a useful high-level summary of Flexcom Wave.